Today we want to continue looking at our sphere from yesterday. So we looked at a sphere centered at the origin with a radius of 3, and we described it in rectangular coordinates, in spherical coordinates, which was right on the money. That was the one that we wanted to use in this case. And now we want to use cylindrical coordinates because we want to make our lives difficult, but not that difficult. So if you recall, cylindrical coordinates is just putting a z-axis on top of polar coordinates. So cylindrical coordinates is just installing a z-axis on top of polar coordinates. We're just putting a z-axis over polar coordinates. Rectangular coordinates are x, y, and z. Polar coordinates are r, theta, and the same z. The z in rectangular coordinates is the same z in polar coordinates. So we're still looking at a z-axis going up, a y-axis going left to right, and our x-axis coming straight out the page. And we're looking at, if there's a point here, x, y, and then we map that up to a point above it. So this point is x, y, z. We're really just looking at the point in the xy plane and putting it into polar coordinates, r and theta. So the z-coordinate is the same in both. Here's our theta. The z-coordinate is the same in rectangular and polar coordinates. Rectangular coordinates puts a z-axis above x coordinates xy, rectangular coordinates, just extends it one more. Cylindrical coordinates is putting a z-axis on top of polar coordinates, and it's the same z. All right, so what this means is that if we have a relationship, if we can turn x and y into r and theta, then we can turn rectangular coordinates into cylindrical coordinates because the z is going to be the same. So the relationship between x and y and r and theta is that y is going to be r sine theta. Oops, I forgot to label the r. So if we make a little right triangle here with theta as the angle, and our right angle will be here, then the y is r sine theta, and x will be r cosine theta. So here we can see how x and y are going to combine, and it's really convenient that we have sine theta and cosine theta, especially because it's really convenient that I picked a sphere to describe in the cylindrical coordinates, because I have this x squared plus y squared, and with x and y being cosine and sine, if I write x squared plus y squared, that becomes r cosine theta all squared plus r sine theta all squared. So we're going to get this cosine squared plus sine squared. So we're going to get r squared times cosine squared theta plus sine squared theta, which is equal to 1. So the x squared plus y squared is all equal to r squared. So what that means is that we can take this and install it back up in our top and bottom half of the sphere. So this is the top and the bottom hemispheres when we solve for z. This is the top and bottom hemispheres. And if I just take the x plus y squared and replace it with r squared, I can write z as plus or minus the square root of 9 minus r squared. So here's how we describe the top and bottom hemispheres in cylindrical coordinates. Any questions? So we're just going to do a coordinate shift. So now if we want to describe the solid, the sphere, in a triple integral, so remember we need an r, an extra factor of r, so that our dv will have 3 lengths in it. So r, let's see, what did I do? dz, d theta, dr. So the r, this is to turn the d theta into a length. That's the why we have this extra factor of r. The function just needs to get converted into a function of r, theta, and z. So the z's, the z is between the bottom and the top hemispheres. So that will go from negative the square root of 9 minus r squared to positive the square root of 9 minus r squared. To describe the entire sphere, we need theta to go all the way around. So theta should go from 0 to 2 pi. And then the radius r should, remember the radius needs to be positive. So we're going to start off at the origin and we're going to go out to the edge of the sphere. So r will go from 0 to 3, the radius of the sphere. Any questions? What would be useful at this point? What would be useful at this point would be to try to adjust your triple integral to be things like that we were looking at yesterday. What if we want just the top hemisphere? What if we just want the bottom hemisphere? What if we want just the right side? How can we adjust so that we just look at the right side? Any questions? So look, try to chop this up into different parts. So what would the definite integral, what would the triple integral look like? Just the top hemisphere. What about the right hemisphere? What about the top half of the right hemisphere? So find the triple integral of these different things: the top hemisphere, the right hemisphere, the top half of the right hemisphere, and then a really interesting one would be, how would we hollow this out? Is it even possible to just hollow this out? So we had a spherical shell. That would be an interesting question. That would be a time when we definitely would want to switch over to spherical coordinates, because we could make a spherical shell. Just, we saw yesterday, we could write a triple integral for a spherical shell just by taking rho, instead of from 0 to 3, from 1 to 3 or 2 to 3. Could we do that in cylindrical coordinates? This might prove tricky, because the z is going from the bottom hemisphere to the top hemisphere. What's going to happen is, if we're in the hollow part, it's going to go from the bottom hemisphere to the bottom of the inside, and then there's going to be this gap until we pick up the top of the inside to the top of the top hemisphere. But then that's going to change, because once we get past, once we're just going up and down and we're in the shell part, then it's just going to go from the bottom hemisphere to the top hemisphere. So think about if it's possible to write a spherical shell in cylindrical coordinates, or do we just need to switch to spherical coordinates? That's number one. The other follow-up integrate the function 1 to get the volume of a sphere. The other follow-up that you would want to do is to integrate the function 1 to get the volume of the sphere. Remember, if we're doing a triple integral and we do a triple integral of the function just 1, then that will give us the volume of the solid over which we are integrating. Any questions? How's everybody okay? Everybody looks stunned. So here are the follow-up questions that you'd want to look at, just like the follow-up questions that we had yesterday in looking at different sections of the sphere. To help you along with this, I have posted, oops, there it is. I put this file in the files section. I had it all called up and then, of course, I closed that window. Let's pause the recording here so I don't have to record me fumbling around looking for a file. Let's pause the video here and talk about next steps.